Uh, so welcome to yet another exciting topic which we would be covering today, and this is on neural networks and very specifically aimed at medical image analysis. So while we have dealt a lot of topics about how features are extracted and what they can be describing over there, and we had done a last class on using random forest and decision tree like learners as well for doing classification segmentation problems. So yet again another exciting one is, can we use neural networks for doing the same thing as well? So I would be starting with a very primitive introduction to what neural networks are, and from there we will be proceeding on to how we are going to actually do it, and there's an exciting demonstration as well using a very small snippet code on MATLAB as well. So this talk is organized where I'm going to speak about what a neuron model is. So mathematically how you define a neuron as in its own parlance, and from there I would be moving on to say what is a neural network and what the neural network formulation looks like, and from there I would be proceeding on to very standard learning algorithm which is called as error backpropagation, which is as of now one of the most commonly used. So there are different ways in which how this error is backpropagated and how things are optimized, and then we have gradient checking and optimization, which is just optimization criteria as to when to stop and what is the final conformal configuration of a neural network where it would be giving you the best of classification or say regression problem. So without much of a delay, let's start with how we define a simple neural model. So say that you have a feature vector which just has 3 dimensions. So I can represent a particular feature sample over there as a vector x, which can have 3 different scalar values, x1, x2 and x3. So these are basically 3 different components which make up, or 3 different features. So now I take these ones and then I want to predict a particular variable which is called as p, and note the fact that I am putting a small hat on top of p because this is a predicted variable. The true state of the variable will be the same value p without that particular hat, and p stands because I am using it as a predictor constraint over here. So now let's have a very simple model which would say that let's multiply each of these observation points over there with a certain weight. So x1 is multiplied by a weight called as w1, x2 is multiplied by a weight called as w2, and x3 is multiplied by a weight called as w3. Okay, now we additionally take another weight called as w0 or the bias, and so you can also define this bias as unity multiplied by a weight w0. Okay, in that case your w0 to w1, 2, 3, they all form down one simple vector which is called as w. Now if I have a summer over here, then my output of this summer would appear something like this, which is y is equal to w0 plus w1 x1 plus w2 x2 plus w3 x3. Now in terms of a matrix multiplication, I can just write it down as a scalar multiplication between a weight matrix, w's, I also take b as a bias term over there, and I take a transpose of all of these x's and unity. So this is going to give me a scalar, a dot product between them is going to give me a scalar value. Now I apply certain sort of a transformation on top of this resultant output over there, which is called as a nonlinear transformation, and this will be mapping my output of this summer onto my predictor, which is p hat. Now this nonlinear function can be of this particular form, which is 1 by 1 plus e to the power of minus y, where y is the input given down to this nonlinear function, and this has a very famous name. This is called as the sigmoid nonlinearity function. Now if you look over here very carefully, so if the value of y is tending towards 0, so you would have basically e to the power of 0, which makes it 1. So the value at y equal to 0 for this function is 0.5. Now if the value of y is a quantity which is very much negative, so say minus 1000, okay, now you get 1 by 1 plus e to the power of minus 1000, which makes it 1 by 1 plus e to the power of 1000, which is a very large number compared to 1, and of so in that case this nonlinearity fnl would actually tend towards e to the power of minus 1000 where it goes, and that's a very low number, very close to 0 actually. On the other way, if you see the upper bound of it, when y tends to a very large positive number, then you will be having this whole thing e to the power of minus y, where y is a very large number tending actually towards the 0, and then this whole function over here will be of a form of 1. So you see that for negative values of y you have a saturation at 0, for very positive values of y you again saturate at 1. So even if your y becomes unbounded in some form, this nonlinearity imposes that your final predictor is always bounded in the range of 0 to 1. Similarly, there is another famous function which is called as tan hyperbolic, and this also has a similar bound, except for it's not bounded in the range of 0 to 1, but it is bounded in the range of -1 to +1. So these are certain kind of nonlinear functions which we use so that our responses always remain bounded. Now from there, let's look into how we can formulate a whole network using these kind of neuron models. So as of now, what we were doing is we take down multiple such input parameters over there, and we are able to predict only one of those output values. But my constraint may be that I want to predict multiple of those output values, and that's where a neural network will form down, that I have a network being created. So in that case, so we take the same simple example that let there be just 3 different parameters over there, and let there be one single neuron which is mapping it to one predictor value P1. Now note, I have taken these weights no more as just W1, W2 or W3. They are now written as W1, 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 3. And this basically stands, the first element is the target where it is being mapped, the second element of the subscript is the source from where it is being mapped, and this is a very standard convention how it goes. And that's by the same reason that your output over here is also termed as Y1. Okay. Now in a similar way, I can map it down to the second node as well, and once I map it down to the second node, I will be able to get down my response from the second node as well, and this will be the form in which it would appear. Now let's say that I have j number of such input nodes, and I would like to map it to k number of such output nodes, and in that case, very typically a weight relation between the jth input node to the kth output node will be mapped as W of k comma j, and you would have a similar kind of nonlinearity, and this is the basic form in which it appears. Now if we look at the total network at any point of time, this is how the picture of the whole network is going to look like. Now over there, for my first input over here, for my first set of inputs and my first element on this output over here, I will be able to find out certain difference which is called as the error, which is I am predicting the value of P1 as P1 hat, and my actual value should have been P1. So there would be a difference between them. Say this is 1 and this comes down somewhere around 0.8. So you have a difference of 0.2, or similar kind of cases might appear. If this is also 1, this is also 1, you get an error of 0. That means you have done a perfect mapping over there. So this function over here, we just will take down accumulation of these errors which come down. Now similarly, for the second node also you will be getting a similar quantity. However, the question is, you are going to get all of these errors for each of them. Is there some way in which we can say about the cumulative error being predicted in this whole network? Now in that, what you can do is, assuming that this is also a vector, and you can actually compute the Euclidean distance between these two vectors. So you have a set of those actual state variables, and you have a set of those predictions which you are getting down from this network. Take down in Euclidean distance, that's going to be a scalar quantity which will be a cumulative error of this network while it's predicting it out. Now keep this in mind, this is a very important step, because this is what we are going to subsequently use in the next stages as well. So this commodity over here is called as the mean squared error, which I am going to take down. Okay. So if I am going to, so I will come down to how we are getting the mean quantity over there, but this is as of now just a square root of the error which we are getting. So the next term which we call is known as error backpropagation. Now what this does is pretty simple. Say you have a network, you had put down certain values of those weights over there. Now you would actually want that this neural network performs in a way such that my error E, which I was computing in the last step, should be minimum. That is my final goal and objective which I need to achieve. However, the point is that how do I select what are the values of those weights such that this network will give me the minimum error, and that's a question in hand. Now we solve it using this method called as error backpropagation, in which what we do is we just compute what is the final error coming down with a particular combination of these weights, and then we will like to backpropagate it or push it back into the network, and then keep on refining the values of these W's such that I will come down at a place when after some point of time, after refining it for a few number of iterations, I should be at a position to get down my maximum performance over there or minimum error. Now for that, what I can do is I will not just be having one single observation of excess, but I will be having a series of such observations. So say in a simple example, I have a set of images on which I can say whether they are some sort of diagnostically abnormal or diagnostically normal. So we will be later on the class, when we do the coding exercises, we would be taking a very simple example in which we are going to take down microscopic images of white blood cells, and we would be predicting whether each of these WBC images over there are cancerous of a particular kind, which is acute lymphoblastic leukemia, or they are not at all leukemic in any way and they are perfectly normal. So this is what we are going to do. So we will be just given images. So corresponding to each image, I can extract a set of features. So that will be, for my first image, my set of features will be x1. So that image will have a state variable, which is either it's normal or abnormal, 0 or 1, and my network would be predicting a certain value. For the second image, I will be having my features, I will be having the state variable over there. Now make a note over there that I have generically used a vector notation for P, but these can be scalars as well. So I can put them as class labels of 0 and 1, or I can keep them as a binary tuple class, in which it will be the first one is the true or false for the first class, and the second element over there is the true and false of the second class. So if it is class 1, this will be appearing in a form as 1 0. If it is class 2, it will be appearing in a form of 0 1. So that can also be a way in which this can be represented. Similarly, I have for all the n number of images. Now what I do is I write cleverly something called as the cost function, which is j of omega, and this is where my this summation over this error comes into play. So what I do is typically for a set of weights, I will be pushing all of these training samples over there, and I would be finding out what is my difference of error computed for each of the sample. Then I take a sum of all of those errors, because that is going to represent my cumulative error in performance of the network over all the samples over which I have as of now pushed forward through the network. Now from there, my objective is somehow I should be able to minimize this cost function, which is the error, because if I am able to get minimum error across all the samples I am using for training, I would be able to get the network which has maximum performance accuracy over there. Now for that, we write down formally our whole objective as the argument of W, in which I get a minimum condition for my cost function coming up over there. Now in order to achieve that, what we do is called as a gradient descent learning, and this whole learning paradigm is defined something like this. We have another variable called as an epoch or k over here. So what we do is, for a certain epoch, whatever is my weights, I am going to subtract the derivative of the change of this cost with respect to the weights over there. Now remember one thing, that j of w is a function of Pn and Pn hat. Now Pn is a constant, but Pn hat is actually a function of all of these x's, because your predictor was over there. Now when you have a function of all of these x's and w's over there, so this function is actually dependent on both x and w. So I can take a derivative of this whole thing with respect to w. So this becomes a finitely solvable problem, given the point that each function which is functionally constituting simple elements over this variable should also be having a finite derivative only in that case. And as you see, all the earlier equations which we have used, they are summations, and there is a certain amount of non-linearity which is also continuous and differentiable throughout the range. Now that's why this comes down as a differentiable quantity, and you can always keep on solving. Now the question is, now that I get it, how do I actually train my network, which is the objective which we are trying to achieve over here during the process of training. So what we do is, we take the same equation over here. Now we would start with some sort of an initial guess of these wk. say that is a random guess at which I land down with the configuration called as W1, and at this W1 I would be getting a certain error which is over here. Now based on this error and solving out this derivative, I can update the value of Wk. Now having updated the value of Wk, there is a chance that I would land up somewhere over here, and this will be my error position. Based on that I am again going to update it. So at each iteration I am going to compute my cumulative error over all the samples I am using for training, and this way I keep on repeating till I land down at a position k, which is the final point where I can actually stop, and beyond this the error is not going to minimize any further. Now this scale over here of change of k's is called as epochs, and this comes down from the fact that within each epoch or within a small age of time I am going to have all the possible changes being taken care of over there. So I use all the samples which are present over there in order to compute my errors and update my network, and then I keep on repeating across epochs. Now let's look at a fun part over here, which is how would this gradient descent actually work. Now we were looking into this graph over here, which is about the cost function varying with the number of epochs, but we were never trying to look into what these weights, what was happening to the space of these weights, because that's where the fun is located actually. Now what happens over there is we will be starting with some random guess. So we have just two plots over here, and we are going to look down simultaneously into both the plots. Now at the first epoch I have this first initial guess where I start. Now that's a pure random guess. Now based on that I am going to update. So I actually got an increase in my cost function, and here I am going to change my position appropriately because my W's are also going to change, so it's a different combination of W's. Now from there I move down to another position. From there I keep on moving till the kth position when I get down somewhere over here, and this now what would happen is if you are going to change across all of these values of W, say you are empirically, instead of training the whole network, what you do now is you take a network and then you possibly point out all the possible values of W's, and then you can actually get a surface plot over there. So say W1 is varying in the range of minus 500 to plus 500, and W2 is again varying in the range of minus 500 to plus 500. So I just change these values in discrete steps over there, and then I would be getting a 2D matrix, which this height of this whole thing will be giving me the surface over this cost function over there. Now what typically happens is that as you are going to look at a point over there, and then you find out the gradient, this gradient was actually del W of JW. So that is the first derivative of this cost function with respect to the weights itself. So it's going to follow the slope along this weight surface and come down to the point wherever this cost is minimum. So that's where this concept of gradient descent comes from. It does not come from the concept that this graph is a epoch versus cost graph, but this is a gradient. It's going to descend along the gradient inside this surface plot of the cost function itself. So on the plot on the particular function of the cost function versus the weight, it's going to follow the gradient along that and come down to a position where this error is going to be minimum, and that's what this whole training is all about. Now with that we are finishing off with the theory, and as a take home message what I would do is I have a pointer. You can have a look into this book called as Neural Networks and Learning Machines by Simon Haykin, which is a very famous book on neural networks. So please have a look through it for understanding theory in much more details. And if you would like to play your hands around, then I have a list of these toolboxes. In MATLAB we have the stuff called as Neural Network Toolbox. The simple command is npr tool. It's a GUI based, and we will be doing the subsequent experiment on this one itself. On Python you can use the toolbox called as Theano, and there is another scientific programming language called as Lua, on which a particular library for mathematical intensive programming is Torch, and within that you can use certain modules called as NN, and NN graph, which we will be looking in fact in the subsequent lecture on deep neural networks, as well as how to play around with them in solving a similar kind of problem. So with that we would be proceeding next to the demonstration on how to use these ones for a very practical problem. Yeah. So this is about the experiment which we will be doing today. So I would be using the ALL IDB dataset for this thing. So as I was telling you, this particular dataset is about leukemic images, and this is a particular condition of cancers within the blood in which your lymphoblasts, which are a type of white blood corpuscles, they actually get cancerous. And this whole challenge is about being able to classify each WBC image into whether they belong to the ALL class or they do not belong. So you can get your data set by signing into the terms and conditions of use over here and download the same thing. So for my purpose, I actually have the whole data set downloaded with me, and this is how these images look like over here. So typically you will be having each of these images which are sort of WBCs, and what they do is they have actually marked each of them with a file name which has an _1 or underscore zeros. So these zeros are the ones which are perfectly normal, and the one which wherever you have a _1 written, they are the ones which are leukemic in nature. And the problem is very simple. You have these image patches, and from these image patches you just have to classify whether this one belongs to an abnormal class or an abnormal class. So let's look into our MATLAB code which does that. So I have a neat script over here, thanks to one of the TAs who helped me prepare this one. So what we do is typically I'm just doing a bit of bookkeeping over here, which is I go down to the path of where my data is kept, and then I'm reading down all the images which are present over there using this directory function, and then just looking into how many images did I read over there. Now from there what we do is typically that I try to create down two different vectors over here. One is this feature vector, which is all my x's, and the other one is my labels matrix over there. Now you remember that in my feature vector what I have is basically 1024 such columns and n of such rows. So for each of them I will be having 1028 different features which are being extracted. Now on my labels, I did tell you that it can be a 0-1 classification problem, first class and second class, and how I can write down is some sort of a tuple. So I can have, for the first class I can have a 1-0 combination, for the second class I can have a 0-1 combination, and that's the way in which we are going to use the labels over here as well. So what I do is I read down one of these images, and then after I have been able to read, convert them onto a grayscale image, and from there I find out certain co-occurrence matrix properties. So we will be computing a grayscale co-occurrence matrix of these features, and then from there we will be finding out what is the contrast of that co-occurrence matrix, the correlation, NHG, homogeneity, and these kind of factors coming up. Now once that is done, what I do is that you can actually now resize this whole image itself into a patch of 32 cross 32, and once that whole thing is done, now what you will be doing is you also along with these co-occurrence matrices, you push down that whole thing, whole image itself as features over there. So each pixel of the image is also a feature as of now. Now later on in the class we will again understand in a bit of more advanced lectures, we will get into fact like how this also helps over here. Initially it might appear a bit confusing from the fact that we were already extracting features, and then why do I push down the whole thing, but there is a beauty which happens with that. Now what we do after that is so this particular bookkeeping over there is just to find out the class labels, because you don't have a separate file which says which image belongs to which class, but it was the file name where the whole encoding was done. So this is just to find out which belongs to the first class and which belongs to the second class. Now from there, once this is done, we have already prepared our data. Now the next part is over here what we do is we randomly shuffle out the data, and the reason for doing all of this shuffling is that we do not want to typically have a certain kind of ordering. So if you look at those images, the first few images were all belonging to the abnormal class, and the last few images were all belonging to normal class. So now if I'm somehow, if I look at the whole gradient descent problem over there, so first I will be training it being very much biased towards the positive class, after that very much biased towards the negative class, which is normal. I don't want to get this kind of a bias creeping into my system, and that's why I would just be juggling around with the order in which they come. So there will be maybe the first one or two of them are from the positive class, then next three are from negative class, then next one is again positive, next one negative. So in any random order in which it comes, which will smooth down the way in which errors are computed and how the weights are trained over there. Now once I have actually made all of this into one single linear array after this random permutation, now what I can do is, this is one place where we were just trying to save it. You may choose to save the feature vectors as well for use sometime later on, because every time you do a rand perm, it's going to randomly permutate in a different way. So you might like to preserve the way in which your ordering was there. Now what we do is, here is where we start defining the network, and it's a very simple command actually in MATLAB, where you can define this as a pattern classification network which just has 100 neurons in one single hidden layer. So if I just want to change, I can just make a comma 10, so that would make down two different layers in which the first one has 100 neurons, the second one has 10 neurons over there. And by default, this whole thing over here is where it's going to use just sigmoidal activation functions. You can again play around with them by just going into net dot activation function equal to and change all of these properties. So you can just look into the documentation on much more details. And then I start with the training, in which what I do is I feed the network, which is randomly initialized. I feed all the features which it has to use for it, and I feed all the labels where it will be using in order to find out. So let's do a very simple run over this. So since this is divided into modular cells, so what I would be doing is I would first evaluate the first section, which is about finding out the features. So now that we have all of the features coming down over here in this feeds, and I also have my labels coming down over here in this label matrix. Okay, so I basically have 260 such samples over which this whole thing has been computed. Now with that, I start with defining a network, and let's train the whole network. So you see how fast this whole training has happened down. So this is where this whole network was created, and you have a very graphical output about it. So we took down 1028 dimensional input, and then we fed it down to 100 hidden layers, and from there it was mapped down to an output which was just 2 vector output. And you can easily see that within this was set down for 1000 iterations over there, and in just 22 iterations or 22 epochs, it has actually come down to the minimum point where it is supposed to saturate. Okay, now let's look into that epoch versus performance graph. And the training over here was based on another energy function which is called as cross entropy. And so you basically have 3 different graphs over here. Now what these graphs do is, basically this blue one is called as the training graph. So we were dividing it into 3 different batches of samples again, and in that a few of these samples were used for finding out the error over there for back propagation. Now based on back propagating and updating the whole thing, we used another set which is called as the validation set, on which we were finding out where should we stop down at a particular point of time. And there is another set which is called as the test set, which is basically used for testing over there, and we don't use that error from the testing in order to do any updates or any changes onto the system. So this is one of them. You can actually click on each of them and have a different look. So you can open up the receiver operating characteristics, and that would typically be showing you for the 3 different sets. So for the training one, what is the ROC, for validation what's the ROC, and for test what's the ROC. And you would also be getting a 2 class problem over here, and for that reason you have 2 different ROC metrics also coming down. Now from there we can also be looking at the confusion matrix, which makes you very clear about how many false positives, false negatives, true positives and true negatives you are going to encounter, and what is the total performance of the system as such. Now if you look over here, the total number of errors which is on the cross diagonal elements, which are the false positives and the false negatives, you actually have a much lower quantity over there, just 5% and 6% and 4.56% of it. Majority of it, which is about 95.4%, is actually a true classification. About 90.5% is actually a very true classification which happens. So you can see that a very simple neural network, we could be training it down just with 100 neurons on one single go, and you have a 90% accuracy on classifying these patches of WBCs into either ALL or they are not. So with that, we come to a conclusion about neural networks, and that's all. Thank you.